Hello and welcome back to Precalculus 1, section 1.8, inverse functions. Now, in a nutshell, inverse functions, the goal of the inverse function is to undo what you do with the function. For instance, if your function of 3 returns 7, then the inverse function of 7 will return 3. It's the undo. We also have to understand that certain things cannot be undone. Sure, you walk in the classroom, turn on the light, you can invert that by turning off the light. You take the sweater over your head, it works out to be wrong side up. You invert the sweater right side up, and there it is, right? The same way it was when it was on you. So certain actions, certain functions can be undone. But then certain things cannot. If you are to shatter the glass or a vase, right, as I used to as a kid, you break it, it goes to a million pieces, you can't glue that back to make it look as used to. Or you're making a soup. The recipe calls for a teaspoon of salt. Now you misunderstand it, right? You misunderstood the recipe, and you put 1 shovel of salt, right? The snow shovel of salt into the soup. Can you undo that one? No, you can't go in and pick out the individual salt grains. It's done. It's ruined. Keep adding the water? Yeah, but then you need carrots and you need everything else. So, no. You don't get to undo certain things. So, the concept in this lecture is going to be the same. Certain functions will have inverse functions. The others will not. Remember that mathematics models all of our existence, everything around us is modeled by mathematics. So certain aspects of the physical reality can be undone, which means they have inverse function. When you push the undo button, it's the computer software which has inverse function in there. It computes certain stuff, and the computer deletes whatever you did that you don't want. Very simple here. The push undo, gone. Right? Very simple. Now, as I said, the cheapest possible thing you can think of for the inverse is to undo what was done, and here it is. F of 3 is 7. The inverse, which has this little -1 on f, the inverse function will take 7 as input and give 3 as the output. So what we essentially do with this inverse is we swap domain and range. Meaning x values from domain with y values in the range. And this is how you find inverse function. So say that your f of x, why are you blue? Say that your f of x is 3x minus 9. Your job is to find inverse. Well, over here is stated exactly what you must do. You are to swap x and y, and then you will follow the algebra. So you will write this as y equals 3x minus 9. Right? We know f of x is y. And here comes the swap. This is that key step where you are changing this into inverse. All you need to now is to fish out y. So x plus 9 is 3y. Divide both sides by 3. And you have your y equals x plus 9 over 3. We write this f inverse of x is x plus 9 over 3. That is the answer right there. That's the inverse function for f of x. And you have this function and inverse pair. 3x minus 9 gives you the inverse function of x plus 9 over 3. You want to test this? Well, let's try a value. It's not a proof, it's just you tried one value. The proof is going to be function composition. We'll see that soon. So let's just verify that this works to some extent. So how much is f of, so check. This is not a real check. Well, let's call it that way, not a real check. So not a real check, but it should do for now. Let's compute f of 5. How much is f of 5? Well, it's 3x minus 9. So 3 times 5 minus 9. That's 15 minus 9, which gives us 6. This means that the inverse computed at 6 must return 5. Otherwise, we're doomed. Well, 6 plus 9 over 3 is 15 over 3, which is 5. We're happy. So that was just a quick calculation. This is not the way you will be checking. This is just for you to also see that the goal of these inverse functions, what they do is they return the original input value. So function computes and changes that 5 into whatever number, depending on the function. And the inverse function is supposed to take that answer, in this case 6, and give you back the 5, the one you started with. Yes?
Can you explain again this part here to the x, the first part, and then you have the 3y minus 9, and how do you get 2x plus 9?
Well, you are solving, once you do the swap, which is this term here, you have to solve for y with whatever witchcraft you can master, okay? So we added 9 divided by 3. It's going to be unique for every function. Later, we're going to do this with exponential functions. Next course is going to do it with trigonometric functions. Calculus is going to do it with hyperbolic functions. So you have to follow algebra. So maybe I should add that as a step over here. Follow algebra to solve for y. So follow algebra to solve for y. That's all we need to know. Let's take a look at the actual way to check. Very important. Way to check if two functions are inverses of each other. Function composed with the inverse needs to give you x as the answer. Inverse composed with the function of x needs to return x as the answer. These are formulas. These are formulas that you are learning, so you are able to check if two functions are inverses of each other. You see function composition, which means you will plug inverse for every x of the original function, or you will plug function for every x of the inverse. If they return x, they are inverses of each other. If they don't return x, they're not. You have to be very careful, because function composition will return something. If that something is not x, the input functions are not inverses of each other. Now, so now the actual check of the previous problem, the real check. We have f of x, what was it? 3x minus 9? And we computed the inverse as x plus 9 over 3. No. Yeah, x plus 9 over 3. Function composed with the inverse of x is function is 3. And now I have to plug in the inverse here, x plus 9 over 3 minus 9. So you see that the structure of the whole thing is f, which was 3 times x minus 9. X is replaced by the inverse. And now we go ahead and follow algebra. 3 will cancel 3, get us to x plus 9 minus 9, and then 9's cancel, and there is x. This is how we check. We can also check by composing inverse with the function. So now we plug in, so the structure is the inverse. We plug in function 3x minus 9 plus 9 over 3. 9 and 9 will cancel, we get 3x over 3. 3 cancels 3, we get x. If you are still struggling to understand what's going on, we can also draw some pretty pictures. We have our domain, which is input. We have a range, which is the output. And we have a member, x, and its image, y, in the range. The function f will change x into y, and the inverse function will go and bring it back to its original state. So that's the graphical representation of what's happening. Here's an example for you to enjoy. Find and prove the inverse of f of x equals square root of x plus 2. I will work on the first two steps so that you guys can pick up if you're unclear. We write y equals square root of x plus 2. And here comes the swap x and y. That is the crucial thing because inverse swap domain with range. So you swap x and y. So x is equal to square root of y plus 2. And your job now is to solve for y, which will give you the inverse. So now you follow algebra from here to get the other thing. Right? So let's take a look, finish this problem off. We square both sides to get rid of the square root. We get x squared is equal to y plus 2, from where y is equal to x squared minus 2, and we claim that the inverse is just x squared minus 2. I asked you to prove, which means check it. You are going to compose f with the inverse, or the other way around, whatever. So f is this square root of something plus 2, and that something is your inverse now. 2 and 2 will cancel, we get square root of x squared, and the square root of x squared is just x. You have to take 2's away first, and then square root cancels the square. All right. Now, if we are to do the same problem with f of x equals, let's say, x squared, for simplicity, we are going to run into a lot of trouble here, because as we do the swap and we square root both sides, note that the plus and minus kicks in, and we get that y is equal to plus minus square root of x. Observe the graph of the input function, and then observe the graph of the output function. Clearly, x squared passes vertical line test, so f of x is a function. Clearly, f inverse not a function, as it fails vertical line test. So now we have this issue, right? Where you look for the inverse, but the inverse is not a function. Do you have an inverse? Yep, it's right there. This is an inverse. You can use it to figure out the values, but the inverse is not a function, and that's important for calculus later on, differential equations, so on. So we are going to have now a whole group of problems where you have the inverse, but the inverse is not a function, so we say no inverse function. Look at the title of the lecture. It didn't say inverse. It was very specific. Inverse function. And clearly that's not a function in this case. Remember that when you are graphing, positive root x is this branch, and the negative root x is the bottom branch, right? Reflects it on x-axis. We learned that in 1-6. Never goes away, guys. All of your courses you're going to take, 1-6, 1-7, 1-8, they never go away. We are going to talk about these three sections when we do polynomials in chapter 2, and when we do exponential and logarithmic functions in chapter 3. I told you again, chapter 4 for trig, chapter 6 in calculus for hyperbolic functions. These three sections will never go away. So now we have this issue, and we see that the inverse is not a function. So what we have now is something that we call horizontal line test. Horizontal line test. So if you apply horizontal line test on the f of x, it is going to fail, pass or fail. So if the horizontal line test passes on the f of x has an inverse function. If it fails, it has inverse, but that inverse is not a function, so it does not have inverse function. It has inverse, but doesn't have inverse function. Be very careful about the words used there. There's a difference between the two. So, if f of x passes horizontal line test, f minus x is a function. If it fails, right, if f of x, if f of x, there are two it's here, so if f of x fails horizontal line test, f is not a function, which means we do not have inverse function. Again, we have inverse. Please look. Fails vertical line test because it cuts, horizontal line cuts twice through it, so it failed, and you can see that this one fails vertical line test, and because it fails vertical line test, clearly it's not a function. The way to fix this, I'll put fix in quotes, is to work with restricted domain. What this means is that when I look at y equal x squared, I ask myself, well, what's duplicating here, right? So I'm not getting the horizontal line test to pass. Well, we have two branches here that are the same, right? They are reflected on y-axis. So if I remove one of these two branches by restricting the domain, domain used to be from negative infinity to infinity, right? All the real numbers. What I'm going to do now is I'm going to kill the left branch, and this is still x squared graph, but what I did is I restricted domain 0 to infinity. This guy is restricted domain. Now, when I do the inverse, I don't have to worry about plus minus branches, because the minus branch, as you can see, is taken away. So now, when I do the inverse, y equal x squared, x equals y squared, square root both sides, square root of x equals y, I do not have the plus minus in this case. So now the inverse exists, and it's just square root of x, and its graph is good old square root of x, only one branch. It passes vertical line test, so it is a function. This is not a key point. It is in your text, obviously, in your book, and you will have few homework examples on this. But this is not a key point for Precalc 1. It is a key point for Precalc 2. When you are looking for inverse functions for trig, sine and cosine, remember that the sine was a wave that infinitely does this. Do you see how miserably this fails horizontal line test? Horizontal line test fails infinitely many times on this function, which means that its inverse will fail vertical line test infinitely many times. It's going to do that. It is not a function. So we have to introduce the notion of restricted domain, and you've seen it here first, right? So you will introduce that notion, and you will be able to define 6 inverse trig functions that play a key role in calculus and differential equations. So this section does not go away. It's time to summarize the entire lecture. We'll do a few more examples next time, but you should be well equipped to do the homework for 1/8. The next class is Thursday, right? So let's summarize. The inverse always exists, but the inverse is not always the function. It is a function where function f of x passes horizontal line test. To find the inverse, you swap x and y, right? You swap x and y. Then you follow the algebra to solve y equals everything else. And then you write f negative 1, right? It's the notation for inverse. And to check if two functions are inverses of each other, to check if your answer is correct, you will do function composition between the function and the inverse, or the other way around. You must get x. There is another aspect that I didn't discuss yet. I'll do that next class, which is graphing. Inverse function and the function are reflections on y equal x line. So there is also a graphical portion. You might run into some homework problems with that. You probably will. Since I didn't talk about it in detail in class, I will start next class with that. I'll answer your questions for homework, and then we'll go on with 1.9. Actually, no, we skip 1.9. I'll review 1.9 briefly, and then it's 110, word problems. Woo! The homework pile is very thin, so thank you for that. I have no work to do, which means all zeros also on your part, but, you know, it's not a free lunch. I will see you all in 2 days. And here, well, some of you I'll see in Rotaract at a meeting before this. And by stream.